Okay, hello everyone, continuing spin dynamics, the second lecture on practicalities of software implementations of simulations that we'll be dealing with from a slightly more theoretical perspective in term 3. And what we'll be doing today is simulating, once again from scratch, from an empty page, a large spin system. And large, I mean 10 spins or so. Without any of the state space restriction technologies that is applicable to bigger systems. That's slightly more complicated algebra for the end of term 3, but we'll just do a straightforward simulation of a system that a typical computer and a fairly typical simulation program can in practice deal with. And because it's a 10 spin system now, we would not be coding some of the things explicitly. We will be using for loops, we will be using arrays. And in practical calculations, it takes a considerable amount of planning and thought to try and code up a program that would, on the one hand, be extensible, that is, it would handle a significant number of different systems, but on the other hand, simple. And so we'll try striking a balance today, and just like last time, I will simply start from the empty MATLAB file and code everything up with comments as we go and explain things as they happen on the screen. So comments again, so 10 spin simulation, myself as the author, function, hello again world. Second time without any input arguments. Just put an end, so MATLAB is happy about it. And the first thing we need to do is to just put in our usual Pauli matrices. So Pauli matrices, sigma x was 0, a half, 0, sigma y was 0 minus 1i over 2, 1i over 2, 0, and the sigma z was a half, 0, 0, minus a half. Once again, we'll be checking whether these things commute correctly before proceeding, just in case to avoid problems later. So sigma x times sigma y minus sigma y times sigma x minus 1i sigma z ought to be 0. So let's save it somewhere else where we saved it before and just run it and see what happens. And well, we get a 0 matrix, so second time round we got it right on the first try. Now, what we now need to do is to scale the simulation up to 10 spins. And probably the best way of doing that is to not actually explicitly code in the number of spins that's equal to 10, but just to make it a variable, number of spins, and let's say n spins equals 10. Okay, so let us now decide where to store those matrices. Now, as it happens, the software support, including in MATLAB, for three-dimensional arrays is pretty poor. And in particular, what's not supported is three-dimensional sparse arrays. And because we will be moving into sparse matrix algebra later in this lecture, we cannot actually just, stack operators in the third dimension. And MATLAB happens to offer a rather neat way of storing almost anything that's called a cell array. And a cell array is an array of anything you can think of. Yeah, it's just a collection of it. And because it's an array of anything you can think of, it's rather easy to adapt for any practical purpose. So we'll be stuffing some operators into there, possibly of different data types, but there we are. So why don't we make some cell arrays? So cell arrays of operators. So our LX operators, all of them, will be a cell array which will have one row and n spins columns, so 10 columns in our case. Similarly, Ly will be cell 1 n spins. There's a comma here, and likewise for the Lz. And spins. So what we can now do is populate those things with our matrices, the ones that we will be making. Okay, so let us loop for n equals 1 to the number of spins. And we will be now creating those operators via Kronecker products. So initially, let's say our Lx will be initialized to just 1, and then we'll cron it up. We'll be making direct products with Pauli matrices as we go and populating those things. So we are now looping over the operators, and for each operator we will have to start from just unit and then cron things up as it goes. So another for loop for k equals 1, again to n spins, and our initial operator, let's say Lx, will be equal to just 1. And 1 is a one-dimensional state space with just one state. It simply corresponds to spin 0. And what we also have to add here at the end is the unit operator. So unit equals 1, 0, 0, 1. Right, so we'll have an if statement here. If k happens to be equal to n, then we have to cron the sigma x Pauli matrix into Lx. So Lx will be cron Lx sigma x. Alternatively, if we're dealing with some other spins that the current operator doesn't specifically refer to, we'll have to cron it with the unit matrix. Lx is cron Lx unit. So what will now happen is MATLAB will build us an operator which has unit matrix everywhere for each spin except sigma x for just one spin. And finally what we'll do is we will add it to our cell array. Now you'll notice a collision of notation here. I've called this cell array Lx and I've called this Lx, and of course they would collide and it would overwrite the original cell array. So why don't we call this Lx current? And MATLAB here offers to rename everything into Lx current, but that's not a good idea, so we'll just rename everything here. Current. And finally, after that operator has been built, we can actually assign it to Lx, and cell arrays are numbered with curly brackets. Lxm will be Lx current. And this will build up that operator and put it into that cell array. Well, we can similarly do it for the Ly and Lz, so I would not write another for loop for that. I will simply just cut and paste things here and duplicate the corresponding lines in the if statement, not forgetting to change which operators we're actually crossing. So if it's Ly here, then it's Ly here, but also importantly sigma y on this end. So z, 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 and finally here. You see, in the general case, things do pretty rapidly get rather complicated from the reading perspective. Y, Z, and Z, and finally we duplicate this line in just a single line, like that. Y, Y, and Z, Z. There goes. Now, of course, we just built everything explicitly and we stored it all in memory. In practice, when you are doing some big software project that has to be memory conserving and has to fit into reasonable sized computers, it's always a good idea to only compute things on demand when they're actually necessary, but here for illustration purposes we just computed everything at once and stored it in memory. Right, so one final thing that we will require in this case is the unit operator that corresponds to the entire system of 10 spins, and of course that will just be a unit matrix, and so we can simply just make it. So we'll close that for loop and we'll call it unit. I just generally use E, and it will just be a unit matrix I in MATLAB notation. Dimension will be 2 to the power of n spins. And if we've got 10 spins in the system, it will automatically be a matrix that is 1024 by 1024, which is the correct dimension for the unit operator in this system. Right, so you see what we've got now. We've got a reasonably well arranged code where we either have comments written out explicitly what the block of the code is, or we have reasonably descriptive names for everything. So Lx, Ly, and Lz are immediately recognizable to an NMR spectroscopist, and then the loop is clearly over the number of spins because this is n spins, and something current is clearly referring to a current instance, and chron is a Kronecker product, and sigma x, sigma y, sigma z are the Pauli matrices, and unit is the unit operator. So any spectroscopist that actually opens this code later on, including ironically ourselves, if we look at this in about a month's time when we've forgotten everything that's been written here, will actually be able to instantly understand what it is that is going on here, and that can be very important because all too often people just neglect documenting what it is they're writing, and far too often you open a piece of code and it's all single letter notation and goodness knows what it refers to. So always a good idea to have these descriptive names everywhere. Right, well, let's just run this thing and take note for now how long this actually takes. You see what we are looking at the moment is matrices which are 1024 by 1024, pretty sizable matrices, several megabytes each, and there are 3 of them per spin, so we've got 10 spins, so there are 30 such matrices plus the identity operator. So this is clearly already not a small calculation, and let's just take a look at how long it takes. Okay, and in MATLAB we can easily see how long it takes if we use this tick and talk. Hello again world, talk, and it will give us the runtime of that file. And the runtime is half a second. So we haven't made any mistakes in the code, not at least any kind of mistakes that MATLAB would immediately recognize as such, but well, it runs for a considerable period of time. You can see it's reproducibly on my, let's say, not an average workstation, it's half a second. And if we have to redo it multiple times, for example, if we're doing some kind of calculation on an ensemble where every Hamiltonian is different, these things rather quickly add up to significant numbers. So what this brings us to is a fairly interesting fact. Let's take a look at one of these operators. So let us say, let's ask MATLAB to show us what are the non-zeros of, let's say, Ly on the 6th spin. And to show us the non-zeros, what we need to do is to use this command spy. And it just plots us a diagram where it has a blue spot in the position where the matrix has a non-zero and just leaves a spot where there is a 0 blank. So let's run it and see what we've got for that operator. There we are. So these little blue dots in here, they refer to positions where the matrix has non-zero. So position, let's say 225, and position 241 has some kind of non-zero. It's probably the order of 1 here or something. But you can see the matrix is of course not diagonal. Life would have been too simple if they were diagonal, but it is certainly rather empty. And if we look at other operators in this system, so at something else, let's multiply something together. So let's say Ly number 6 times Lx number 1, so some kind of two-spin order, and take a look at what that is. It'll also be pretty sparse. So it's got non-zeros in a different location, but in fact most of the matrix is 0. Now this is really important because the number of elements in this matrix is 1,000,000. To store a double precision number, what we need is 8 bytes if it's just a real, and 16 bytes if it's a complex number. So just looking at this matrix, just to store it, we need 16 megabytes of storage space. And it's mostly zeros. Now the procedure that recognizes that spin operators are mostly zeros, and in fact only stores and only manipulates non-zeros, is called sparse matrix algebra. So let's take a look at what a sparse representation would be. What I'll do is I'll take something simple. I'll take sigma x and I'll just print it. And then I'll tell MATLAB to make it a sparse matrix internally. Sparse sigma x, and tell it to print it again. And let us see what happens in either case. So I'll just run that thing and see what there is. Now look at the fairly peculiar difference here. Sigma x printed us the matrix. And yes, there is a non-zero element here and there is a zero element here, but other than that it is just a matrix. However, sparse sigma x has given us a pair of indices and a value. That is, it only stored explicitly the non-zero elements of the matrix. And in the case of a 2x2 matrix, it's not a very efficient representation, because you see, here it had to store just 4 numbers, here it has to store 6. I mean, okay, these are integers, but still, for a 2x2 matrix, there isn't much of an advantage. However, the advantage is considerably greater if we look at a matrix that is 1000 by 1000. We'll print Lx, and we'll print sparse Lx, let's say for spin 4, and let's see what we've got. So what will now happen is there will be a kilometer of output for both this and this, but the output would be rather different. So let's run it. There's our big pile of zeros being printed, and there's an instant printout from the sparse representation. So if we scroll MATLAB up several screens, we've got a long list of zeros here, and they're stored explicitly. Each zero occupies a spot in memory, whereas the sparse representation only stored non-zero elements and their corresponding indices, and you can see that there are considerably fewer elements. And the command that actually tells us how many non-zeros there are is nnz. So if we take a look at the total number of elements in this matrix, and then we take a look at the number of non-zeros in there, you'll see what I mean storage-wise. So num_l gives the total number and nnz gives the number of non-zeros. So running it again, the total number of elements is over 1,000,000, the number of non-zeros is just 1000. So if we store that matrix as a sparse matrix, we save a factor of 1000 in the required memory. Now clearly, for big spin systems, this is an obvious thing to do. And thankfully MATLAB operates transparently on either full or sparse matrices, and so once we've converted something into sparse notation, we no longer have to worry about doing operations with it, because everything's supported transparently for both types. Right. The second thing that we need to know about is The simple fact that once we are in a sparse representation, mathematical operations become considerably faster. Of course, there's no point multiplying zeros, and in full representation what the processor would do is honestly crunch through millions and millions of zeros and produce millions of other zeros, and each multiplication will be as expensive as a floating point multiplication. In the sparse representation, however, what will first happen is the algorithm will carefully sort elements that actually do match, and only for those elements that actually match up on the index list, multiples will be computed, multiplication will be done, and selectively the resulting elements, only the non-zeros, will be written into the resulting index. So it's even intuitively obvious that the number of multiplications in both cases will be vastly different. So why don't we tick-tock matrix multiplication and make a quick comparison. Tick, and let's say Lx 4 times Lz 2, tock, and then we will multiply their sparse representations. So I will first convert them into sparse notation and then tick-tock some multiplication. So let's say, for a quick comparison, A will be sparse, Lx 4, and then B will be sparse, Lz 2, so same operators in both cases, and then tick A times B tock. And well, let's look at the timing. There we are. You can see we've gained 3 orders of magnitude in the storage space, and we have also gained 3 orders of magnitude in the runtime. So again, for speed purposes, for large spin systems, using sparse matrix algebra is essentially mandatory. The crossing point, however, for this advantage happens at about 5 spins. You see, as we saw for a 2x2 matrix, there wasn't much advantage in using sparse algebra for 2x2 matrices. It mounts as the matrices get bigger, and the crossing point between the gains in efficiency and the complexity of various housekeeping operations associated with sparse representations happens at about 200 by 200. So if we are running a system with 5, 6 or 7 spins, we might just as well run it in a dense representation. But if it's bigger than 7 spins or thereabouts, it becomes necessary to run it in a sparse representation unless you really are prepared to wait the age of the universe until the calculation completes. Now, to be fair here, there is one other way to accelerate matrix multiplications that is available in MATLAB, which I should briefly mention for completeness sake. This is GPU computing. Many of you have got fancy graphics cards in your computers, particularly from NVIDIA, which I'm sure many of you are using to shoot up some pretty scary monsters. But what those cards can also be used for is crunching numbers. And so what we'll now take a look at is multiplying matrices on graphics processing units. And again, I'm only doing it in the hope that MATLAB will eventually support sparse algebra on GPU. It doesn't at the moment, but if for some reason you have to multiply very large dense matrices, which might happen in solid-state simulations where density matrix very quickly becomes dense and there's no point using sparse representations because every element is non-zero, in that case it might actually help to multiply things on GPU. And MATLAB's programming is again quite transparent in that respect. The only command you have to execute is the command that initially uploads the matrix to your graphics card. It's called GPU array. So let's again say our A will be Lx number 4, and then our B will be Ly number 3. Let's tick-tock some multiplication. Tick A times B, tock. And let's now send them to the GPU and do that again. So A will be GPU array. This sends the matrix to the graphics card, A, and B will be GPU array B. And we'll now multiply them and see what happens. Tick A times B talk. And now this isn't just a multiplication, this is the instruction to the graphics card to multiply those matrices. The result will be stored in the graphics card. It requires a separate command to actually retrieve it. And let's see how long that one takes now. You see, about a factor of 3 to a factor of 4 faster. If we run it again, it might even be a little bit faster. Yeah, there we are. So we gain about a factor of 4 in dense matrix multiplication if we are multiplying very large matrices on the graphics card. To be fair, my graphics card is the latest NVIDIA that is available at the time of writing, so if you have something that's a year old, it might give you a factor of 2 to factor of 3 in the speed up and floating point complex multiplication. But there goes. The advantage can be quite significant, and it's certainly worth considering. We are not implementing GPU algebra in Spinach at the moment because everything in Spinach is on sparse algebra, and unfortunately MATLAB does not, at the time when this lecture is being recorded, support sparse multiplications on graphics cards because of the random memory access that's associated with sparse indexing, and unfortunately graphics cards do not at the moment really properly support low latency random memory access. All access and simple straight matrix multiplication, of course, can be made sequential, and this is why they can rather well be implemented in this graphics hardware. But there we are. So as soon as matrix dimension exceeds several thousand, we are in a good position. Okay, let's continue with our writing. So now that we have the basic operators that we require, actually I doubt we'll ever need the unit operator in there. Let's make our Hamiltonian. So, Hamiltonian. Again, in practice what you'll have will depend on the details of the system that you're actually simulating. What I will do is just cook up a set of essentially random parameters, random chemical shifts and random J couplings. So let's say chemical shifts. So Zeeman, frequencies will be rand n normally distributed random numbers, 10 of them, and they usually have a standard deviation of 1 when you just request them from MATLAB. Now let's multiply that by about 1000, so we get them scattered rather well, and also multiply them by 2 pi. So we now have random distribution of chemical shifts within 1000 Hertz range, or well, plus minus 1000 Hertz. We'll also put some J couplings, scalar couplings. It will be a matrix, so 2 times pi, well not 2 times pi, just pi times rand n 10 10. So everything will be J coupled to everything in this case, and let's say we put J coupling between 0 and in an RMS way about 10 Hertz. So those will be our J coupling. Of course, in any practical calculation, this is a synthetic example, but in any practical calculations these numbers will come out of the literature. Somebody has recorded the spectrum, assigned it, got the parameters out, and will be using those parameters. Be careful to avoid double counting. Of course, there are elements in the upper triangle of this J matrix, there are elements in the lower triangle. You have to watch how many times you count them and so on. But again, in a synthetic example, it is, in our case, irrelevant. So, okay, let us put together the Hamiltonian. But before we put together the Hamiltonian, what we'll do is we'll actually transition our entire infrastructure that we had here before into sparse algebra. And for that, because everything in MATLAB is transparent, the only thing we need is to sparsify the original Pauli matrices. Make them sparse, like this. Sparse. And the same applies to the unit matrix here. It might not save us an awful lot by way of speed, because really this is a fairly small problem. all things considered, but it will certainly save us the memory footprint. Right, well, let's run it actually. I vaguely remember it took about half a second up to this stage previously. Let's see how long it takes this time around when everything is sparse. So if both operands in a matrix operation are sparse, the sparsity is inherited, so it will be transparently transferred through the cron operation. Let's see how long it takes now. So tick-tock, hello world, unbalanced expression, I've missed the bracket somewhere. Let's see where that is, here. Let's run it again. There we are, 0.03, so we actually have gained about a factor of 15 in speed. Quite a serious achievement, as you can imagine, from just, putting the word sparse in front of the matrix you are starting with. So yes, do please seriously consider using this when you are running very big spin systems. Right, so with that in place, let's continue building our Hamiltonian. So 4 n equals 1 to the number of spins. Interestingly, you see we've coded everything in general, so why don't I comment this out again? And if we want 11 spins, suddenly nothing changes here. We just have 11 spins. So it will take slightly longer to compute them, but there we are, we actually have them. And interestingly, what we can do now is things like 15 spins, and then if I look at the size of the matrices that I'm generating, Lex 10 for example, those will be huge matrices. So let's take a look at how big that is. It might take a while to build them, but they're 32,000 by 32,000. If it were a dense matrix, it would not have been possible to store it in the memory of my workstation, because 32K times 32K is, well, a few gigabytes. Let's get us back to 10 spins, which is reasonable for our purposes, and continue building the Hamiltonian here. So, Zeeman interactions. And for high-field NMR, they would only include the LZ operators, so let's say those are the isotropic shielding parts. What we would normally do is initialize our Hamiltonian to 0 somewhere here, reallocate Hamiltonian, array, H is sparse allocation, so that MATLAB doesn't have to reallocate the memory every time we add to it. 2 to n spins times 2 to n spins, and then the expected number of non-zeros. Now, there happens to be a rigorous upper bound, we published the bound recently, on how many non-zeros a Hamiltonian can actually have. And it is of the order, very roughly, of n spins squared times the dimension of the Hamiltonian. So what I'll put there is that number. But if you're interested in the exact bounds, they're very rarely reached, because not everything interacts with everything by far in a typical magnetic resonance system. But just in case, let's allocate enough memory to hold everything. So n spins squared times 2 to the n spins. 2 to the n spins. I could never remember which way the operations priority are in MATLAB, so I just bracket everything just in case. Okay, so we've got our Hamiltonian pre-allocated, so let's add all the Zeeman interactions. H will be H plus Zeeman frequency number n times the LZ operator number n extracted from the cell array, and those would be our Zeeman frequencies. And now the couplings, scalar couplings. I will do a double counting here, just thinking that the elements of this matrix here have been appropriately doubled where necessary. But of course, one thing that we don't have in liquid state NMR is that spin is not coupled to itself. So we better zero the diagonal of this matrix, or put an if statement in here to avoid having spins coupled to themselves effectively, because what would simply happen is we'll get the unit operator if we take Lx squared plus Ly squared plus Lz squared for a single spin, and we don't really want to uniformly shift the energy of everything at once in the system. So for n equals from 1 to n spins, for k from 1 to n spins, and then if n is not equal to k, we say h is h plus scalar couplings times L x from spin n times Lx from spin n, spin k, plus the same term for Ly plus the same term for Lz. So copy, paste, paste. So there's y here and y here, and then z here and z here. And you can see if we didn't have them as sparse matrices, this would have been quite a lot of sparse matrix multiplications. And that would build our Hamiltonian. Let's see that we haven't made any mistakes here. MATLAB tells me that I'm not using this variable, and the reason I'm not using it is I haven't typed it right here. So now everything seems to be alright, and we'll build our Hamiltonian this way. Just as a point of curiosity, let's take a look at how dense it is. We have a pretty densely interacting spin system where everything is J-coupled to everything with a random J coupling. It's highly improbable that such a system would actually occur in a real-life liquid state NMR simulation, but even for such a system where everything is coupled to everything, as you will see in a moment, the Hamiltonian is in fact very sparse. So let's take a look. Something we've missed. So there's n spins here rather than spins, and let's run it. Inner matrix dimensions must agree, so we have missed the dimensions somewhere as well. So now we are in a debugging mode. We need to find out what the hell is incorrect and where the hell it is incorrect. So we've got Lx, Lx, so they're both matrices, Ly, Ly, Lz and Ls, Lz. And MATLAB complains that matrix dimension is not right somewhere, so why don't we actually look at the dimension of the matrices that it is complaining about. So it's clearly on this line that it has to match, and we've clearly missed something. And we probably are alright multiplication-wise because we did multiplications before. What we have a problem with here is probably the Hamiltonian dimension. So let's take a look at the dimension of what we are trying to add to it here. So size of that thing. And then let's take a look at the size of our Hamiltonian. That will be something that MATLAB is expecting from us. And run this thing again. Matrix dimensions must agree. So 1024 everywhere. So clearly some dimensions are correct, but others are not. And let's see where we actually are getting this wrong. So somewhere the multiplication doesn't quite do what it's supposed to be doing. So let's then print the sizes of every matrix that we've got. Size Lxn, then Lyn and Lzn. And let us actually comment all of this out and simply print the dimensions just in case we've missed something. Like that. So you see, I'm not scripting it. This is real life coding, and we are doing a real life debugging on a living simulation, as it were. So let's see what dimensions we got. Everywhere correct, so we've got all the things 1024 by 1024 everywhere. So no problem there at all. Everything should be multiplied the right way around. So we're doing things correctly everywhere. So let's see what the problem then is. Let's see if we're able to do this multiplication in every possible case. Copy, paste, get this loop out of here and into here. Got that, and so it's all closed, and let's see whether that works as intended. Yep, everything got multiplied together, so we are actually doing it correct on the dimension side of those operators as well. So something else is a problem. Deleting this now and uncommenting our original code. So there's that if statement. Oh yes, scalar couplings. I have forgotten the index nk, and clearly it wanted to multiply a 10 by 10 matrix of scalar couplings into a 1000 by 1000 matrix of operators, and that is certainly impossible. So we now figured out what the bug is. Just the indices were missed on the scalar coupling array. So now that we figured out what's going on there, everything should be running correctly. So let's remove all the unnecessary indentations everywhere and run that code and take a look at the sparsity of the resulting Hamiltonian. There we are. It's a pretty picture now, so we've got quite a few non-zeros because there are quite a few interactions in the Hamiltonian, and if we zoom it in, we'll find out that, well, the pattern is quite intricate. There are many non-zeros in there, but you can see it is still mostly empty. Even in a system where everything is interacting with everything with a strong J coupling, the Hamiltonian is still mostly zeros. So the advantage of having sparse matrix algebra is therefore quite great. And if you look at the number of non-zeros here, it's just 24,000 out of a million, so it's just 2%. Only 2% of elements are non-zero, and therefore less than 2% of multiplications will actually in practice have to be done. Now we are coming here to an important point, is that this sparsity only pertains to the actual operators. Very unfortunately, if we take the exponential of this Hamiltonian, that one's going to be dense. And actually, if we start taking powers of the Hamiltonian, so pi, for example, h to the fourth, we will quickly notice that the matrix becomes considerably denser. See? It's mostly non-zeros now, and so the advantage of sparse multiplications starts to diminish. So for that reason, it is imperative in quite a few calculations that we keep our matrices as sparse as possible. Now let's take a look at matrix exponential though. So let us pick up our Hamiltonian that we now have and compute a propagator. So P will be xpm of minus 1i times h times time step. And let's take a time step that, well, let's put it that way, hasn't been judiciously chosen. So our time step will be of the order, if we've got a few thousand hertz, let's take a millisecond time step. So a time step that is rather long on the time scale of the system evolution, and then spy our propagator, spy p, and see what happens when we look at that exponential. See, it is taking considerable time, and what we are getting out of it is, again, a pretty dense matrix. Let us, however, take a small time step and look at it again. So not 10 to the minus 3, but 10 to the minus 6, and we'll only look at the elements of the matrix which are actually significant. So we'll look at those elements that exceed a certain threshold, let's say 10 to the minus 6. So with a small time step, let's see how many significant non-zeros are there in the propagator. And it turns out not that many. And if we start slowly increasing the time step, this is really quite a small time step, it's impractically small, so let's say 10 to the minus 5. Again, very sparse. Let's go to 10 to the minus, not 10 to the minus 4, but maybe 5, 10 to the minus 5. See, it starts getting denser, but it's still not a full dense matrix. So the lesson to learn from here is long step propagators are dense, and the advantage of sparse matrix multiplication vanishes and memory gets overflown pretty quickly. So taking these huge elephant steps is quite rarely actually a good idea. And we've just seen with our own eyes that small step propagators are sparse, and they save memory, they save multiplications, and ironically in quite a few practical situations it is for that reason considerably faster to take, let's say, 10 long time steps than it is to take one big time step, because of the associated memory footprint with storing the propagator for that big time step. But okay, for our practical purposes, what we'll now do is simply choose a propagator that approximates the system dynamics well. So our time step will be 1 over norm est, the estimate of the norm of our Hamiltonian h. And I'm using norm est here because h is large and the calculation of a matrix norm is an expensive procedure, but we don't really need to have that norm extremely accurately. An estimate would do, and that will be serviceable as our time step, and so this is our time step now. And if we look at the density of the resulting propagator, we will find that it is in fact very sparse. See, norm est warned us here that it didn't quite get to the accuracy target, but we only need an estimate, so it's not a big deal. But the propagator is sparse, just 30k elements out of a million, and so we can now run with that propagator without the fear of overflowing our memory or doing some extra unnecessary multiplications. Right, well, from this point onwards what we can simply do is take the code from our previous function, which we have made sure at the initial period in time when we wrote it that it was portable. We commented it well, so we can now simply open it, our original hello world function, and well, take a look at the simulation here. You see, here's our propagator, here's our pulse function, here's our coil function, so in principle we can just cut and paste all of that, and we should be able to adapt it without difficulty to our new simulation. So Ctrl V, this pastes our spectrum, and clearly the initial state will have to be modified because it's no longer just LZ and SZ, it will be a sum over all SZs in our system. So our row will just be a sum of those matrices. So what we'll do is write a quick for loop. It's actually possible to do this sum in just one line, but it's perhaps a rather convoluted function, the cell mapping. So I'll just do it with a for loop in this case. So our row, first we have to do a spalloc, just allocate it as we would do an ordinary operator, and then just add together all the LZs that we have, and essentially we can just adopt this particular for loop here with a little bit of rewriting. Our row will be our row plus LZ on the spin n. So that's our initial state. Our detection state will be similar. We have to pre-allocate our coil because it is now a sparse matrix. So there goes, and we have to write a for loop which is quite similar to the one here, except it will be referring to the coil state, and it will be the coil state plus this little thing on every spin. Ctrl V, so Lx on spin n plus I Ly on that same spin n looped over n. So these are our coils, then the pulse operator will have similarly to be generated from here. So I'll just put it as a pulse Hamiltonian here, pulse Hamiltonian, and make something similar to this. So it'll be HP allocated. HP is HP plus, we are pulsing on Y here, so it will be Ly, and instead of this sum we will have HP in here for the pulse. Time step we have already declared, that's our time step, that's the XPM. Now by default MATLAB's XPM returns a dense matrix, and it's important that we actually sparsify it. So we'll say that this is sparse. There are better ways of computing exponentials of sparse matrices. One of them is implemented in Spinach, but we simply don't have the time to go in this kind of fine detail here. Sparse. And what we'll also do is something that we call garbage collection. That is, we will actually kill all the elements of these propagators, which are smaller than 10 to the minus 6. So p pulse will be p pulse, element by element multiplication by a logic matrix abs p pulse bigger than 1e minus 6. I wouldn't explain why, but this destroys all the small elements of the corresponding matrix. And it's important because it improves the memory footprint. Evol. So there we are. So we built the propagators and we cleaned up propagators. Right, well, let's see if we can now manage. So we've got a simulation, and here is the simulation. So we apply our pulse to our original density matrix, and then we're running it for 2000 steps, and we are tracing it with the coil state, and we are then zero filling it to 8K, and we are multiplying it by a window function as we did in the previous lecture, and we are plotting everything. And just so that we don't have to wait too long and always have an idea about what happens in our simulation, I will just ask it to plot the number of steps every time it makes a step, so that we know where we are in the actual simulation. And well, the little sign in here is yellow, but it's only yellow because I haven't terminated this with a semicolon, so it will be printing to the console, and everything else looks like it's going to run. So we've got the Hamiltonian here, we've got the initial state, nowhere to make any mistakes really, same for detection state, same for the pulse operator. This is standard stuff from our previous code, and so is this. This is just a standard line for the cleanup operation, and everything else we haven't even changed. It all remains as it is. So let's just run and see what happens. I wouldn't tick-tock it, it might take a while, so let us just calculate it. So something's going on. It complains about the fact that the sparse 2 norm is not available. Line 75, so our time step, it has to be norm est. It really is available, the sparse 2 norm, it's just expensive and it defeats the purpose of using sparse matrix, so MATLAB, in its wisdom, tells us to read the manual. So norm est, and this should keep it happy. So something's happening, it complained about norm est not converging, and it's making our steps slowly, one by one, and you can see it probably will take a while. So 10-spin simulation is in this case taking, well, about 1 step a second on my workstation, so we clearly wouldn't want to wait here for 2000 steps, so why don't we make it, for just didactic purposes, a slightly smaller spin system. So terminate the operation, and now what will happen is the beauty of our universal coding everywhere. The only thing we really need to change is the n spins here. So let's say 7 spins, and I wasn't very careful here, so this should be equal to n spins as well. N spins, n spins, and everything else should just flow through, because we never explicitly said it's gonna be 10, we always said it's gonna be n spins, so the calculation will now just proceed with a 7 spin system. And yep, considerably faster. Of course, 2 to the n scaling, we cannot really in Hilbert space simulations work around that. So let's see what we get. And that's our spectrum. And we clearly haven't put the J couplings to large enough a value. Let's make a few J couplings really, really large, so that the spectrum actually looks complicated enough to be worth simulating it. So 10 times bigger J couplings everywhere. Let's say it's a carbon spin system. Same calculation again. There we are. Big and complicated. So there, this is how you do a general simulation in Hilbert space. I will not in this lecture course go into the peculiarity of simulating Liouville space systems. This is really way too far. We will cover the theory in term 3, but much of Liouville space algebra is implemented in spinach, so those of you who are interested in really sophisticated relaxation theory simulations, please go take a look. But again, this is our simulation which has been built from an empty page into something, as you can see, pretty sophisticated. And well, you can go into the literature, pick up some real parameters, enter them here, run the calculation, and it will actually produce you precisely the spectrum that you see in the literature, assuming that you've set all the parameters right. Okay, that's it for today, and I'll see you in term 3.